Alrighty, welcome to ECE344, operating systems. So, well, before we even answer the question, why would we even take this course, let's figure out who I am. So, I'm John, your instructor. See my last name? Bit of a disaster, huh? I guarantee no one can actually pronounce it. I couldn't pronounce it properly until I was about 25, took a trip to Iceland. Some nice Icelandic man looked at my passport, looked at me, he's like, how do you say your last name? And then I said it, and he's like, no. So, yeah, don't know how to pronounce my own last name. So, for the purposes of you and me and everyone else, you can just pronounce it Elfson. So, I'll help you a bit with that. So, yeah, bit of a mess. So, Elfson. And how to spell my last name. So first start with elf. Not Christmas yet, but soon-ish. Then add a sin, Elfson. That's how you can say it. Perfectly good way to say it. Much easier than the Y and the O. And if you need to spell it for some reason, you just take the L and the F, shove it over, and then in that hole, you just put a yo in there. And then boom, you can spell my last name. Hopefully you don't have to, but just in case you do. So just Elfson or John or whatever. Yep.
There's like this echo.
Yeah, there's some weird echo here.
Do you have a lot of bytes or something? I'm not sure.
No, I just have one. There, is that better? Slightly better. Yeah, I just turned the volume way up because everyone was loud and I didn't know how loud I needed it. So there, that's a little bit better. Okay, cool. All right, so let's dive into our first question. Why would you take this course? So, understanding operating systems will make you a better programmer even if you don't actually write operating systems later in your career, because from my point of view, there's only two types of software. So, you either write software that interacts with the operating system or you're writing an operating system. There's no in between. Most of you probably will be in the first category, which means, everything interacts with the operating system. It's important to know how to actually use it and use it properly. So it doesn't matter what programming language you use, you'll be using an operating system all in the same way. This course will be specifically in C, but you can take everything you learn in this course and apply it to whatever language you want. They all interact with the same operating system. So, some important URLs for this course. Some of you have already done this. So very important to sign in to compeng.gg. That will just take your Toronto information and then you can connect your Discord account and your GitHub account, and that's what we'll use for this course. The lectures I just post publicly on my site, so you can go ahead and grab them from that URL. Everything should be linked on the Quarkus page, so you don't actually have to do this. Quarkus should just link you to everything public and private. The labs are at that URL, and like I said, everything else will just be on Quarkus. So, like I said, the labs are using GitHub, discussion is using Discord, and I stream everything on YouTube. Hopefully you still show up, but if you are sick or whatever, I live stream the lectures as I'm doing them. So if you're sick, you can stay home and don't have to worry about missing anything. So, again, connect both your accounts to the compeng.gg stuff. It'll join you to the Discord server, set you up with an invite to the GitHub organization, and then you can go ahead and start working on stuff and discussing. I see a lot of you have already kind of started doing that, so that is great to see. So, the big thing about Discord that people don't like the only thing I don't like, it's otherwise overwhelmingly positive, is there's no anonymous messages like Piazza. Well, during the summer, we fixed that. So if you don't want to ask questions on Discord because it's not anonymous, we created a command for you so you can go ahead and ask questions anonymously, because, well, a lot of you use Discord. You might not be, I thought Discord usernames would be anonymous enough, but apparently you guys are friends or something, which is weird. So you kind of know each other. So there's this. You can just do /anon and then type your message, and then it'll show up just as it's sent by the bot, so no one will know who you are. don't abuse that because I know who you are. So if you like do something very, very inappropriate, I know, but it's a pain for me to even figure out. So for all intents and purposes, you will be anonymous to even me. So that will always work in that current channel. I see some of you have already figured out how to use that command. So there's already been some anonymous messages already. So it's good to see that that was actually a good thing to do over the summer. So lecture attendance, still important. It's a lot faster to get feedback from you, clarify if anything's unclear, and for me to get passive feedback from you too, because if I say something and you all look very, very confused, I know that I probably screwed up somehow. So we'll also have live coding examples. I'll be able to explain any happy accidents. I will do more or less whatever you tell me. That will include breaking my computer, which is fun. If you break my computer, you get, I won't say you get a prize, but I don't know, maybe we'll figure something out. So if there's anything else I can do to make attending a better experience, let me know. Also for faster questions in the lecture too, if you don't want to put your hand up and like physically ask a question, I have the Discord chat, the section 1 right beside me, so you can actually type in Discord too and ask questions that way. So evaluation for this course and boring stuff that's in the syllabus. So we have 6 labs, 1 lab set up, and like lab 0 is basically set up, so that's already live. So you should go ahead. I even made a Quarkus announcement for it, so that's due on September 9th. Other than that, labs are every 2 weeks. Lab 1's really short, so it won't take you that long at all. Labs are basically worth 4% each. There is a midterm worth 25%. Tentatively for October 10th, some of you have already told me you have conflicts. You have like 3 exams on that day or something ridiculous already. So yikes. So we will not have it on that day. We will come up with another day. So that's why I put tentative, because scheduling midterms here is pretty much just like pick a day and see what happens. There's like no central way to do it, which seems really weird, but whatever. But so we'll try and space it out like that so that you actually have your midterm after the, or that doesn't interrupt your fall reading week. That is new for this semester. And then other than that, we have a final, basically labs every 2 weeks. All right. So academic honesty, so you can study together, discuss concepts in Discord, don't post any lab code, don't publicly post your code. If you have similar code, you can post that, that's fine. Cheating, not tolerated, it will only hurt you. A lot of this is like figuring out why something happens, not opposed to just making it functional. You should understand what's actually going on. And it's a software course. Really easy to tell if you like airdropped your file to someone else and then submitted it. Please don't do that. That ends up with like a very awkward conversation with me. Then you have to have a conversation with the department, and that's if everything goes well. And it's just a horrible, horrible process. If you really, really can't just do a lab, just take the L, take the -4%, and just carry on. Like, you're just gonna make both of our lives really, really very difficult. And if you have some extenuating circumstances, we can figure it out. That's not just you cheating, okay? So we can take up the lab later, doesn't matter, I'm free or the TAs are there to help you. So there is a recommended book. It is not one you have to buy, it's online. It just complements the lectures, all the exams and everything. You should be able to do from just lecture content and looking at past midterms and finals for practice and all of that stuff. But it's there if you want. It's available online just to supplement what you already know and just reinforce concepts that are in the course. This course will also be done in C, so if you need to brush up on C, there's a C programming language book by the authors of C, so you can have that as another resource if you want, but hopefully we all are fairly familiar with C from like 105. So if you need some practice to brush up on stuff, well, definitely brush up on your C programming and debugging. We'll have a optional debugging exercise that you can do to just kind of help you along with debugging. You can do printf debugging if you really want. It's not really that imperative in this course to use something like GDB. It's more imperative to like think about what is actually going on and like logically deducing what's actually happening with your code and what's going wrong. Being able to convert between binary, hex, and decimal, I mean, might help you a little bit, probably not that much. Just different ways to represent a number. Knowing what little endian and big endian is, probably you should know what that word kind of means. Won't really be super relevant in that course. And the big one is what people get really tripped up. So memory, it's just byte addressable, and you should know that a byte is how many bits? Anyone? 8. I heard someone start saying 7. That's not good. All right, 8 bits to a byte, and memory is byte addressable. So that means you can address 1 byte at a time. And addresses are basically like numbers. So, you know, there's address 0, address 1, 2. Sometimes we just represent them in hex. But other than that, like memory and pointers, they're just addresses. So you're just where a byte is in memory. So that usually trips people up, but just memory, byte addressable, every different number is a different byte. So throughout this, please provide some feedback. This is a challenging course. Please let me know if anything is unclear. Over the years, we put effort into making the labs a lot shorter than they used to be, while still, you know, meeting all your learning objectives. So, you know, instead of like an 80-hour lab that takes 2 weeks, these ones hopefully take, you know, maybe 20 instead of 80 hours. So should be much more reasonable. And because this is an operating system course, you can ask lots of interesting questions about software. All programs, no matter what, interact with the OS. So even if you have questions about, you know, someone else's program, programs you've written before, how they really work, you can go ahead and ask it in this course, because we should develop the tools to actually answer what the operating system is actually doing when we run our programs. And I promise you, by the end of the course, you will be a better programmer. So, what does an operating system do at the most fundamental level? Well, it just manages resources. So we've probably seen a diagram like this. We developed applications in like APS 105, your C applications. That was just an executable that you ran. Well, that was interacting with the operating system, even if you didn't know it. And then, well, in a course like 243, where you did like some assembly and things like that, well, that was interacting directly with the hardware, and it didn't really tell you about the operating system. So this course kind of links those together. So the operating system sits in between your application and the hardware. So whatever program you're running, it's figuring out what hardware it should actually run on, what CPU it should run on, you know, what memory it gets, you know, where to access storage, things like that. So it kind of ties the other software courses you have together. So in this course, there is 3 core concepts. One is virtualization. So that's just sharing a resource by mimicking it and then pretending that you have multiple copies of it. So we'll see that come up very, very shortly. The second is where your brains will start to melt. So this course starts off very, very hard. Like there's a lot of information really quick. And then after the midterm, it kind of chills out a lot. So don't worry if it moves pretty fast. We'll have time to recover and ask questions. Like it will introduce a lot of new things that seem a bit foreign to you. So concurrency is definitely one of those. So that's handling multiple things happening at the same time and trying to synchronize all of that. And then the last, which will be the very chill period, is persistence. So how we actually store data on a hard drive, how we make it consistent, even without power. So here is one of my favorite software quotes that I got introduced to in like 4th year or something, so I'm introducing this to you now in 3rd year. So all problems in computer science can be solved by another layer of indirection. What does that mean? It means we kind of just generalize the problem and make it easier, and then we solve that problem instead. So our first abstraction or layer of indirection, we kind of use those terms interchangeably, is something called a process. So we probably know what a program is. So a program is just a file containing all the instructions and data required to actually run that program. And then if we need to represent that a running program, well, we call that a process. So a process is an instance of a running program. So if we think about what needs to be in a process for it to run, well, we probably know a CPU has registers. Well, if we have, multiple processes running on our machine, and they were all using, I don't know, the same set of like 32 registers, well, you could imagine that they would just clobber each other and it would just be complete chaos. So every process needs its own independent set of registers. So this is where virtualization already comes in. So each process would have its own set of registers that is unaffected by any other process. So if you change, I don't know, RAX or something like that, or whatever you name the registers, then if you change it and your operating system does something weird like run Chrome or run another process, then whenever it comes back to run yours, your register value is going to be the same thing. So it would have something like virtual registers, and then, well, we should all know like where variables are stored in our program. So there's either the stack or the heap. Everyone kind of know what a stack and a heap is, hopefully. So stack, that's where all of our local variables are. So if we have a function and we go int x, x lives on the stack. And then if we malloc memory, that memory that's mallocked, that lives on the heap. So those are the two regions of memory for our process. So that's right now at least everything we need to have in our process. So let's have our first question where things will start going off. So how are we able to run two different programs at the same time? So for example, you're a 105 student, you write hello world, and then you have another program that like counts up every 1 second, or I don't know, you're also running Chrome. So how does, let's say, memory work with running those two processes at the same time? So in your process, if you have, hello world, and you have a variable for whatever reason, and you print that memory address, well, then can you just kind of guess a memory address and guess like, I don't know, Chrome's memory address and start accessing its memory? Or how does that work? So any guesses how we can run two programs at the same time without any issues? Yeah. Virtualization. What are we virtualizing? Memory, yeah, we have to virtualize memory. So we could probably think of some different scenarios why we would have to have virtual memory. So every process has its own view of memory that's independent. So let's have a little thought experiment. So, well, if we just had a big block of memory, we might be able to think, oh, well, one thing our operating system could do is just allocate a different stack for each process. So like, here's Chrome stack, here's your stack, and the operating system figures out where in physical memory they should go, and then the operating system just tells you, hey, Chrome, use this address, hey, you use this address. But there would be some issues with that because, well, if it just gave out physical addresses, then you could just kind of ignore it and be like, okay, well, you gave me this address for my stack. I'll just use this address and maybe it's Chrome stack, and then I can start messing around with Chrome. And then there would be a whole bunch of security implications and everything like that. So that is one of the issues that would present itself that if we just used physical memory. And then global variables. So you might think global variables are like this magical thing, but really all a global variable is a compiler picks an address, and the compiler picks it. And when you compile your program, the compiler just picks a random memory address, and then that's where your global variable lives. It's not any more complicated than that. So you might think some crazy allocation stuff is going on. You know, the compiler's so smart. No, not really. It just kind of picks a random address and then hard codes that address in, and it just makes sure whenever you access that global variable, it always uses the same address, so it's always the same memory location. If that wasn't the case and we didn't have virtual memory where each process has like an independent view of memory, well, then if you had multiple programs running at the same time, they would each need its own like physical addresses kind of siphoned off so that you don't promise not to touch them, and you kind of like have to register them. So maybe this is our view of physical memory, and we have two processes and say, hey, process one, you only use these physical addresses and nothing else. And then process two, you only use these physical addresses and nothing else. And then you just trust that they just stick to that and don't go over the boundary or anything like that. And like they might just have to register their addresses with the operating system or something like that, so that you know that that set of addresses is set aside for them. But then this would quickly go out of control because, well, you have like Chrome and Firefox. Chrome uses like gigabytes of memory, so maybe Chrome, it just gets half of your memory just allocated to it, where those are addresses Chrome can use. Maybe Firefox gets what's left, and then suddenly, well, there's no room for other programs now. So if you want to try and register a new process to run, too bad. If you want to run multiple copies of Chrome, too bad. There's lots and lots of problems with this. So we can illustrate that I am not lying, that virtual memory is a thing, by having a little demo here. So here, let's switch to this. All right, we can see in the back, see this text, it should be okay. Yep, thumbs up. All right. So we have this program. So this program, first off, let's see how good you are at C. So static int global equals 0. Anyone tell me what static means? Yeah.
It doesn't change?
It doesn't change close. Not
yeah, only accessible in this source file.
Yeah, so static in this case. In C, there's different statics with different meanings. If there is a static in front of a global variable, it basically just means I can only access this global variable in the C file. Why? I don't know. I didn't design the language where static means like 3 different things. So static in this context, that's what that means. So it's just a global variable called global. It's an int, and I can only access it in this C file. And then I have main. So in main, I create a local variable, so int local equals 0. And then while 1, or while true, I just increment the local, increment the global, and then I just print off what their values are, and then I go to sleep for a second. So if I run this program, if I can type, I should see local 1 and see it count up over and over and over again. So if we didn't have virtual memory, what would I expect to see if I go over here to another terminal and I run the same program? So if I didn't have virtual memory, what would I probably see? So let's see where account is.
Add on top of whatever this guy's in.
So add on top of whatever this is. So if I launch another thing of the program, it will start counting from 38 or whatever it is now. So who thinks if I launch another instance of count while it's already running, it will just resume from 55 or something like that? Like no one? All right, who thinks it restarts from 0 or 1? All right, a few more. Who thinks that global will still be counting up and local will reset to 0? A few more with that. All right, let's see. What are we at? Like 77 in the 70s? So now, if we run it now, it just restarts at 1, right? It's another process. So process is just an instance of the running program. We're running that new program. one process is not aware of the other process, so they don't share anything, and this is done by the operating system. So if they did kind of conflict with each other and they're both accessing the same like memory, well, you would expect the count to maybe skip one and go up by 2, so maybe, I increment and then it increments and then I print, but we can see that this one's just happily carrying on while the other one is running, and they have no effect on each other. So let's make sure, because we argued that, hey, the operating system should just give the local variables different addresses, in which case that would make sense, right? So let's just print off the address. Printf, so the address of local is equal to, let's make the compiler happy. So void star, that's just C's way of saying it's a pointer. I don't care what it's pointing to. Local. All right, so there I'll print off the address of local. So that's just the memory address that holds the value of that local variable. So now if I run it in this, whoops, I have to recompile it, of course. So now I run it, I get that kind of ugly memory address, FFFFF D64 501 BC. So now let's go, what did it get up to? So it's hovering around now at 15. So I'll launch it again, and I'll see that it's blah, 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 something AC. So they're different memory addresses, right? BC, this one ends in BC, this one ends in AC. So it could still be the fact that, hey, my operating system's just kind of giving me physical addresses and I can just do whatever I want with them. So let's also print the address of, oops, caps lock is on. Let's also print the address of the global variable. So I will, whoops, recompile. And now I can see that, I got a different memory addresses for local, so it appears to be somewhat random. The operating system's just kind of figuring out where it should be in memory. And then the address of the global is 440030. So I will launch this one, and guess what? The address of the global is exactly the same for both of them. But while I'm running this process, global is equal to 10 right now. If I switch back over, this one's all the way back up at 30. So this is proof positive that there is such a thing as virtual memory. So every process is accessing memory. Every address it gets is completely independent of any other process, even if it is the same address. So that the value at that address is definitely different in both of the programs. So again, here, what global's up to 62, and in this process, it's at like 42. Even though it's the same physical, well, it looks like the same physical address, but we can kind of deduce now that this is actually a virtual address. So they have no effect on each other. And you will figure out through this course how to actually implement this and how the operating system actually maintains this illusion. So everything is just, most things are virtualized on your computer, whether or not you know it or not. So any questions about that or anything silly you want me to do for this code, or are we all okay with it? All right, I think we're more or less okay with it. So there's some evidence that, hey, virtual memory is a thing, and that will be one of the more complicated topics in this course when we actually go about how it's actually implemented. All right, so what we find, the address of the local was different between the two processes when they were both running at the same time. But turns out, I'll give you a spoiler on that one, the operating system, it could have been the same, didn't really matter. The operating system actually randomizes that as a security feature, so malware just can't guess random memory addresses, which we'll get into a bit later too. And in this case, the address of the global was the same between the processes because, well, a global variable, the compiler just picks a random address and then that's where your global variable lives. And it's up to the operating system to figure out how to actually get memory for it. So what else might we need for a process? So we have like virtual registers, and then we have virtual memory, and that would contain like our stack and our heap and our globals and everything else. So can we think of anything else we might need for a process? Stack pointer, so that would still be memory, right? So that would still be under the category of virtual memory. Maybe the operating system needs to like manage that, but the stack pointer would be in a register, right? So that's kind of covered in our virtual registers or virtual memory. What other resources might your process use? Has anyone ever used the internet? Yeah, maybe some networking. Has anyone ever like opened a file?
I/O.
Yeah, some I/O, some other stuff. So that would all be thrown in that process abstraction. That's everything the operating system needs, all your resources your program actually uses when it's running. The operating system has to keep track of them. So right now, we can forget all that. We'll eventually build it up as we go through the course, but those are some of the things you have to look forward to. So for now, this is our view of a process. It has its own virtual registers and its own virtual memory, and virtual memory is where the stack and the heap live. Whenever you run your program, it becomes a process, and each process is independent of each other. So if you make a change in one, it doesn't affect the other. So that's why you can have a bunch of instances of Chrome open or Firefox or what have you. So you will have access to all the example code in this class. So there's a materials repository located at that URL that you should have access to. The instructions to compile everything are always the same. So you just go to the current lecture directory you're interested in. You type meson setup build. It creates a directory called build. And then to compile the code, you just do meson compile build. Or you can just see what I'm doing in the lecture and just copy it. But we'll see, this is kind of like a representative program. So if you have any questions about this program, please ask. This is like kind of the style of C we'll see in this course. So we're going to write a program that uses I/O a little bit and actually opens a file and then reads the first 4 bytes and tells them what it is. So here we go. So here is our program. So we'll start reading it from main. Main, we're going to have it take some arguments from the command line. So it woc have like an argc and an argv. Hopefully, can anyone succinctly tell me what the type of argv is in plain English? Or in like C&Es or whatever you want to call it.
Argument vector.
Sorry?
Argument vector.
Like what is the type of argv, which would, yeah, they kind of call argument vector.
Array of, in this case,
Yeah.
vectors.
An array of characters, close. Yeah, an array of, yeah.
Array of strings.
Yeah, an array of C strings, which are just like an array of character pointers that points to the first character in the string. And then, we should know that all C strings are null terminated. So whenever you hit the null byte, that means it's the end of the string. So what this does, checks that you actually type in 2 arguments. Otherwise, it will just return from main with int inval, which means, hey, you have some invalid input. And then we're going to use this function that it's okay if you haven't seen this open function before. That's basically a way to interact with the operating system and say, hey, please open this file for me. This process would like to use it. So it just opens a file given by the name of the second argument, and then it opens it for reading. So we have this function called check error. Most functions we're going to use in this course, they have documentation, and they all behave more or less the same, where if they return -1, it means there is an error. And in this course, unlike other courses, you probably definitely want to check for errors. So I wrote this little helper function called check error, since they mostly behave the same. So I check the return value I get from open, and then this other message is just like the error message, just in case something goes wrong. So check error, oops. Check error, all it does is check the value. If it's not equal to -1, then nothing bad has happened, so it'll just return. Otherwise, it will store that error, that current error number into a variable, print off the current, like some debug information, and then exit the process. So if I do something here, let's close that. So if I do something like read 4 bytes and then the second argument I give it is a file that doesn't exist. So let's just say I pound my fist on the keyboard and I run that, then I'll get an error, no such file or directory, because open returned an error. There's no file called ggf or whatever I typed. So any questions so far about this? Okay, so other things it's going to do. So it's going to declare a buffer. Buffer is just some memory I'm going to use for the operating system to go ahead and fill in some values. So I'm only going to read 4 bytes from a file, so I set aside a local array. I'll call it buffer, and then make it 4 characters wide, so I only get the first 4 characters. Then I do this read function that takes a file descriptor. You don't know what that is, don't worry about it. Basically, whenever you open a file, it'll just give you a number that represents that file that you can do things with. So in this case, one of the things I can do is read from that file. So in this case, I'm going to read 4 bytes into this buffer variable. So it's going to assign values to each of those array slots. That will give me the contents of that file. And then here I have a and then it returns the number of bytes it actually successfully read from the file. So just in case the file only had like 0 bytes or 1 byte or something, I'll know about it. So then I have a for loop that goes over every byte I read from the file. It just stores that wherever it is in the array into a variable called byte, and then it checks. So hopefully you might know what ASCII is. Hopefully, it's just numbers representing characters. So I know which ones I can actually print. So if the number of the byte that it's stored there is greater than 31 and less than 127, it means it's something you can actually type on your keyboard. So I'll just go ahead and print it as a character. And then otherwise, I will just print that byte as its hex number using that horrible format specifier that looks really ugly. But basically, it's just 2 hex digits. So if I can't print it out. And then I'll check for error. I'll try and close the file. So using this, I can go ahead and read 4 bytes from a file. So you will quickly find out that how computers work is basically by magic. And that is what things are literally called. So most files, the only way your computer actually knows what that is stored in that file is someone just hard-coded some values there, and then if you read those specific values, you just assume that the rest of the file is formatted as like a PDF or whatever. So I can let's try and read the first 4 bytes of a PDF. Hey, maybe that's something. So the first 4 bytes of a PDF, it's a %, and then it starts with PDF. So literally any PDF file in the world starts with the characters $PDF, and that is literally called file magic. So the only way your computer knows that, hey, that PDF file is an actual PDF file is it reads the first 4 bytes, and if it starts with that, it assumes it's a PDF. So You can feed it any garbage. There's lots of exploits you can do with PDF implementations where you can just feed it a bunch of other garbage that's not really a PDF file and get it to do whatever you want. So other things we can look at. So let's see. So we can be meta about this too and read the first 4 bytes of the read 4 bytes program. So like your executable is just a file too, so I can read the first 4 bytes of that and see what it is. Maybe you think it has like, based off PDF, maybe it has like a %exe if you've ever heard of that before, or something like that. So let's figure out what it is. So it is hex 7F, and then it starts with ELF, or ELF. Nothing to do with me. But literally any executable file you have, if you're using Linux and oddly PlayStation, will start with exactly this byte sequence. So we've probably all used ls before, so I can check what's the first 4 bytes of user bin ls. Well, it's the same thing. It's 7F, ELF, and ASCII. So any program you run, going to start with that. That is the magic of the file. And then your operating system, if it starts with this magic, it knows it's an executable file, and it can go ahead and figure it out. So any other questions with that or things you want me to look at? Yeah?
So what does the byte 0 represent in a way? Because in the PDF, I was seeing the percentage sign.
Yeah, so the question is, what's the byte 0 represent? So that just represents the value at byte 0, so like the first byte of the file. So that's just whatever character is stored there. So it just happened for PDF, it's like an ampersand or percent sign, and then for an executable file, it's something we can't type on our keyboard, it's 7F, and then it's ELF. But that just happened to be what it is. So everything's magic. There's no sane reason they picked percent sign PDF. They could have picked whatever they want. Just as long as everyone agrees in the world, then we're good. All right, anything else we want to inspect or any other questions about this? Yeah?
Why for byte 0 to print like 4 characters?
Oh, so the question is why for byte 0 and the other one did I print 4 characters? So I have it printing like a single character if I can represent it at the keyboard, but if it's presenting like 4 characters, it means it's just a number I can't represent. So it's just showing us the actual value. So the value of that byte is 7F, which, anyone have a hex thing? It's like some, what number is that? 1, here, let's go to Python. So 7F is 127. So it's just 127's there instead.
Like, why didn't you like 20? Was it like that in the?
Yeah, so here I have in my code that if it's something I can print, I'll just print a single character. If it's something that I can't represent as a single keyboard character, I'll just print the value in hex. So yeah, so I could just have it print not in hex, I could have it print in decimal or whatever. It'd just be the decimal 127. Yep. All right. Anything else or any other fun files we can go at? Yeah, things aren't that special. What is it called? Read 4 bytes. So we can see, everyone's probably heard of like the standard C library, right? Well, the standard C library is just represented by a file somewhere. If I can find it on this operating system, it's usually called libc. Okay, never mind. I don't know where it is on this machine. Okay. All right, any other file? Apparently I can't find the standard C library off the top of my head. But spoiler alert, it's an ELF file as well. But you can go ahead, you can run this on all your favorite files, figure out what the magic is on them. You can try and figure out what they are. Let's see. We have an EPS file. That's not terribly exciting. Yeah, we don't have any other fun file types. The rest of them are just plain text files, which don't start with any magic. But, you know, we could go ahead and verify, I don't know, the first 4 bytes of the read4bytes.c, but it's a plain text file, so it should just be the first 4 bytes of this file, which would just be, you know, hashtag, if you want to call it that, I and C, so we can make sure that that works. So yeah, we get hashtag I and C, that's the first 4 bytes of our C file. So C files don't have any type of magic. They're not like in some binary thing. They're essentially just one big C string. All right, any other questions, fun things I can do? All right. So only got 5 minutes anyway, so here. So this is hello world. So if you have a very keen eye, you can tell the first 4 bytes of this file. Well, it starts with 7F, and then if you have your fun hex to decimal, and then you look up, you know, the ASCII codes for all the different characters, you might find that this is ELF. Again, this will be the only time you have to look at anything this ugly. You don't actually have to like convert between hex in this course or like know the ASCII things by heart. It's just fun little things I'm doing right now, not terribly representative of the course. But this is actually hello world in an executable that you can actually run on Linux that is very, very short. In fact, the number of bytes here is like it's less than 200. It's less than 150, I think. And if you run this, it will print hello world, which for some reason is even shorter than hello world in C. So I would argue that this is the first hello world that you should see because this is how a computer works. That's a joke, okay? Like, if I showed this to you in first year, you'd think I was crazy. Probably think I'm crazy now. But we'll go over this in the next lecture, how this actually works, break down what the operating system's actually doing with this in order to run it. So with that, just remember, I'm pulling for you. We're all in this together.